All right, welcome back, everybody. So today we're going to be taking a look at an update on a project that we did pretty recently, and that's going to be our particle SOP with LiDAR interaction. We're actually going to be taking a look at how we can extend the interaction from this project to take in multiple sensors. I've had a couple people ask me, can I use this with Kinect, or can I use this with another type of interaction? And the whole point of TouchDesigner is that it's actually really easy once you have a network set up to be able to swap out different components of it and keep the procedural workflow intact. So what I'm going to be doing today is going to, here we are, exactly where we left off, that particle SOP and LiDAR interaction tutorial. And what I'm going to be doing today is adding two new types of interaction using a Kinect sensor and a leap motion sensor. So if you guys haven't checked out the first part of this tutorial series, I highly recommend doing so. I'm not really going to go over any of that stuff. And as you can see, there's a decent bit that's built out here. So yeah, without further ado, let's jump into things. So I'm going to start by just going through a real quick overview of the network so that we can get back acquainted with things. And then we will start switching things around. I'll also note I had some comments that my volume wasn't high enough. So I am now, I believe, maxing out the gain on my mic. Please let me know if this is any better or if I need to continue iterating on that. Okay. Okay, so we've got our project. This is our main project component. If you'll remember, we went through a GitHub externalization workflow. So we actually have externalized all of these toxes. We have a controller that does not too much besides having a reset button, and you can see that we're just calling our project extension here, saving externalized toxes. So those are all saved as we're going. Our perform, pretty self-explanatory. Our LiDAR component, which we're actually going to be not touching too much today, and we'll be replacing a lot of that functionality. And then our particle SOP generative component, which you'll see also has an extension. So we have as much of our functionality and extensions as possible. Here we're doing some interactivity mapping. We have our particle system set up, and then the good old render and post. So the great thing about TouchDesigner, and the reason that it is such a powerful tool, is because this modularity allows you to really easily sub in and out components. So what's actually happening when the LiDAR was interacting, if you remember, we actually piggybacked off of our panel select functionality. So the whole way that this or this component works is just by allowing interactivity via the panel. And then when we were using our LiDAR blob tracking, we were just simulating, as you can see here, simulating a click on our panel. And this simulation is what gave us the LiDAR interaction that looked just like the mouse. Now, not every interactive system might be set up this way, but for those that are, this provides a very easy way to switch out the sensors because we can just use some other input to simulate this click. And whether or not we're simulating the click on the panel is really irrelevant because this modularity, and most importantly, the way of thinking about substitutability as almost like another tool in the palette, extends way past this use case. So yeah, this use case makes it very straightforward, but the higher level concept is one that will serve you well no matter what your use cases are. So long story short, what we need to do is, because we have all of this set up to simply interact via clicks, our first step and the easiest thing is going to be to just grab our sensor data from our new sensors and see what we can use from that sensor data to actually simulate additional clicks, which sounds like it should be simple, and it probably will be. So let's go take a look at that. Now, I am going to, what do I have on this LiDAR component? Yeah, so I'm just going to create a new base. And I'll call this base Kinect. And then I will jump inside of it. All right, so there are, as I'm sure everyone is aware, two different ways of accessing the Kinect data. There's the Kinect top, which is, going to be first this depth, and then there's obviously a bunch of other stuff that we can do here. For right now, though, I'm going to use the Kinect chop because that is going to be the most straightforward. So the Kinect chop is going to grab the skeleton data, and what we can do is basically use the skeleton data to be able to position ourselves and essentially use the skeleton data for, let's say, like a user's hand to be able to position our mouse. And then we just need some way to actually have there be like a click, right? Because we don't necessarily want there to be just like always active tracking. So the way to do that, or a way to do that rather, because there really is going to be a lot, is with depth. So for example, let's start by just doing this. We can select hand. So we'll select this chop, and from it we'll select the hand channels. And I don't actually want the tips, so I'll exclude those. And then for right now, maybe we'll just grab our hand R channels, and then I'll rename them using pattern matching to TX, TY, TZ. Now, as I'm moving around, you can start to see what's happening. So our XY positions, pretty straightforward. And then the Z position, also pretty straightforward. First thing we need to do is map these a little bit. Now, I have a component that I'm going to use for this that I'll include in my talks file for those on Patreon. If you are following along and not a Patreon subscriber, then basically all this talks is doing is taking a trail. It's looking at the range for the parameters. Like for example, it's looking at TY being from minus 0.5-ish to maybe 0.5-ish, and then rearranging. And so then it would say, take like a math and then rearrange from negative 0.5 to 0.5 to 0.1 on TY. And then so on and so forth for the rest of the inputs. I plan to do a tutorial about this whole thing at some point soon, but for right now it is a little bit out of scope. So yeah, in interest of keeping this brief, I'm just going to include this in the project file. And yeah, so the way that we'll use this is by selecting our channel TX, clearing the table, and then listen, and now I'll move my hand in the X direction, and now you can see that it grabs the range, and now basically the input is being automatically remapped from the input range that it listened for and kind of got via me acting in real space, and I'm mapping to 0, 1. So we can do the same for ty, like this, and then for tz, we can do something similar. And so now, you see the channels at the bottom, we have a nicely remapped, smooth, processed data feed coming from our skeletons. So I'll call this processed hand R. Just like that. Cool. So now we have all of this, and maybe let's go back to our other component here to remind ourselves of what needs to be done. So what we're trying to boil all of this down to is getting channels that we can call U and V for our positions, and then an L select. So if I go split this top and bottom, and then I'll make this a panel. All right, so now we can interact with this via the click and at least see what's going on. So as we can see, our U and V is the position, but nothing actually happens until we click. So at least for right now in our current setup, we have to translate our connect interaction into a click. So what we can do for that is using a depth cutoff. And I'm going to go through this. I guess I'll just get rid of this. Close. And close. Yeah, there's a couple ways. I'm going to go through another way after this. So just bear with me for the time being. But I think what we can do is I'll rename this to UV and I'll select so we have some naming consistency. And now what we have to do is replace our L select channel with something that is going to flag when our TZ channel is close to, but not exactly equal to 0. So, I don't know. I'm going to say maybe something like 0.25 maybe for me. So I'm going to use this logic and say off when outside bounds. And then my bounds will be 0 to maybe 33 for now. And so now my Z, and I guess I should select maybe just the Z here, TZ. Yeah, so now we have this binary click that happens when my hand gets close. Do a trail and wire these both in, and then you can see that as my TZ gets lower, then we have this. Okay, so it's a little bit noisy, and that's honestly because this is not really probably the best way to do this necessarily. But that's all right. I'm gonna keep going for now to illustrate this point. So then we can just replace our TZ with this TZ. And so now we have a UV and an L select that's going to be activated. And actually, one possible way that we could also look at this that might fix our problem a little bit is to use a trigger and trigger on decreasing values, say at 0.33. And then we can have a re-trigger delay of like 1 second maybe. And so that way, and then we can turn off all of these, turn off the attack too. And so now, I think this might work a little better. So now we just have our trigger and yeah, so that is working better. If we contrast it to our logic, we can see that our trigger is actually much less noisy and is a more true representation of when we are first kind of crossing that threshold. So let's use the trigger and not the logic. And then I will rename this to out1, just like that. Now, in my particle SOP, I can, instead of pointing this to my LiDAR component, actually bring in another select. I'll go up here, I'll give my Kinect a global op shortcut. Come in here and we'll say op dot connect dot op one, just like this. And so now here we'll be selecting our Kinects. I'm going to do what I probably should have done in the first place. And call a null sensor data and then repoint these chops that are referencing my select LiDAR at there you go. And so now I can just point this select right up here instead of my LiDAR, and let's see what happens. Aha, so we had a renaming issue. So that's fine. Just can fix that naming issue. So sorry, what was going on there is that it was looking for a channel named active to rename to lselect, and so there was no channel named active because I had already named it lselect in my Kinect. And so I guess what I could have also done is in this rename, call this active instead of lselect, and then in here, this is all working. So we're getting an error. No attribute simulate click. Interesting. Okay, and so this is the issue. So we're getting an error when we try to do that interaction that's saying our container comp has no attribute simulate click. And the reason for that is because in this extension where we actually have the simulate click functionality that we wrote last time, we're referencing the U and V of the blobs component, which is actually not what we are looking at right now. So we can update this a little bit and make it more modular. So instead of self dot blobs, how about we say self dot, well, I guess you could do two things. We could either allow us to just pass some variables into the simulate click function. And then when we call it here, we could just call it and pass in the U and V. That's probably what I like to do. The other thing would be to actually point this, like change this self.blobs member and point it at our sensor data null instead of at this operator. But what I think is probably better is to do this. And so now we can just pass in U and V like that. And this equals 0 is going to be a default. So if you don't pass in a U or a V, that U or V is still going to exist. Which is important because we didn't have any variables or parameters in this function beforehand, right? And so if I have it somewhere that I forget about, like in an extension or a dat somewhere, and I'm calling simulate click without variables, it'll throw errors if I just do this, because it's going to then need a number or a variable to be passed as parameters for the function to work. But by giving the function parameters default values like this, we can eliminate that problem for ourselves. And then again, we'll just remove that. And so now we're passing simulated clicks through from simulated click locations rather through from our invocation of the function. So So we get rid of that error, and now what I want to try and do is pass in our U and V parameters here. So I will say null 3 and the U channel, and then null 3 on the V channel. Like that. So let's see what happens there. Press 1, clear everything. And then let's see what happens. So did not work. We got another error. And we are actually getting the same issues here. So what is going on? And it's saying we don't have an attribute simulate click, which normally means that there's some like syntax error or a naming convention error. Let's see. Let's customize this component and look at, aha, there we go. So something must have happened where my extension got like disassociated. So what I'm going to need to do, I think, is maybe initialize this extension again. And now maybe it works. Aha. Okay, so I just had to reinitialize that extension. And now I'll press 1 again. And now we can see that as I'm making different dots with my Kinect in different places, that there are indeed different interactions appearing. So okay, so now we have those click interactions, right? But we maybe want to be able to like have our hand move and have the particles follow. Now, the reason that's not happening right now is because we have our particles following. If I open this up, our particles are following when we click and hold down. And we can see there's something kind of weird happening because my mouse is now jittering all over the place. So there's two things we need to fix. One, we need to fix that. And two, we need to have some secondary activation threshold for when Z is being clicked and held, basically. So we want to persist a 0, 1 if Z is continually underneath this activation threshold. So that is probably going to be our logic, actually. And I'll take this trigger threshold, turn the logic to off when outside of bounds, take the trigger threshold, and I'll reference that as the top bound. So now our logic is going to be on whenever we are underneath our trigger threshold, which in our case is going to be equivalent to a click and hold. So I will rename this, and I guess I'll name it hold. And then I will merge with the rest of our data. I will come in here. So we can verify first that the click part is still working, so that's good. And then part that we need to figure out, if I open this and make it smaller, here, part that we need to figure out is what happens on the click and hold. And it looks like that is this one. Aha, there it is. So that's what's going on. I remember now. We have these attractors, which are being created from our points, or there's this surface attractor, which is tracking the mouse or our simulated Kinect in this case. So this rename for switch 1 input, this one. This is the one that we want. And to add our mouse data there, or sorry, our Kinect data there, we can select this Kinect channel, hold, and then just wire that into this math. And so now, when our hold is 1, it is equivalent to us clicking and holding, which means that then our attractor is going to follow our Kinect position, and then the particles will follow the Kinect. So now we can see we've got some of that object tracking, which is great, but we can still also do the clicks. So we can click by, and moving our hand close a little bit. And then we can also govern the particles and have them actually come and chase our Kinect as well. So that is pretty good for a demonstration of Kinect interactivity. I think I'm going to pause here, actually, out of interest of time. And so I'll say thank you to all of my Patreon subscribers. You guys are continually the best. I really appreciate all of the good words and support from everybody. You can see this tracking me in the background a little bit. So thank you guys so much. Next time we'll go through kind of the same process, but repeated with a leap motion, so you get a sense of one other way to possibly do things. And then, yeah, hopefully you guys will have a strong basis for understanding how to modularize your own workflows so you can take in pretty much any sensor data that is available.